What is the quantum chromodynamic gauge invariant Lagrangian? Quantum chromodynamics is a theory of the strong force. Field theories are written down mathematically in terms of Lagrangian, otherwise known as density. The fundamental particles which interact with the strong force are quarks and gluons. Gauge invariance is a symmetry of a theory under a particular set of transformations. If you look at the QCD Lagrangian, you can pick out what a few parts mean without doing any of the math. You see the letter psi there. That represents the quark fields. The psi is actually a vector where the 6 components are the quark flavors: up, down, strange, charm, bottom, and top. That whole first term is just a sum of the Lagrangians for the individual quark flavors. All the flavors have different masses, so the M is actually a 6 by 6 diagonal matrix containing the quark masses on the diagonal. Now, looking at the second term, the quantity F is related to, but not exactly equal to, the gluon fields. The mu and nu are Lorentz indices which run over the four space-time coordinates, ct, x, y, and z. And the j is an index which runs over the 8 kinds of gluons in the theory. So, all in all, this theory contains 6 quarks, 8 gluons, and the interactions between them. The interaction term is cleverly hidden inside the operator d, which is called a covariant derivative. A lot of this is probably still Latin, but you've picked a really deep pool to dive into. If you're learning about gauge theories for the first time, QED is much simpler. And if you are still trying to get an intuition of what gauge theory is, that's where I think it's better to look at QED instead of QCD. In fact, you can even just look at the subset of QED, the theory containing only electrons minimally coupled to photons. The Lagrangian for this theory looks the same as the one linked above, but it's simpler for a few reasons. First, instead of 6 fermions, there is 1, the electron. Second, instead of 8 massless vector particles, there is 1, the photon. Third, and most importantly, the form of F is simpler, and the gauge bosons don't self-interact. Gluons interact with other gluons, but photons do not directly couple to other photons. So that makes doing computations in QED easier than in QCD. Not to mention, the coupling constant for QED is generally small, 1 out of 137, so QED can be treated in the permutation theory. The QCD coupling constant is large, except at very high energies. So you generally can't use the permutation theory for QCD. Anyway, looking at the QED Lagrangian, the field strength tensor F is just a random equation where A is the electromagnetic potential, in other words, the photon field. The simplest example of a gauge transformation is shifting the potentials by a constant. You know from introductory physics that only differences in potential are physically meaningful, so shifting the potential doesn't affect physics. The field A changes under gauge transformation, but the object F does not. In fact, this whole Lagrangian is invariant under gauge transformations, even under a more restrictive class of gauge transformations called local gauge transformations. The invariance of the Lagrangian under a constant gauge shift implies that electric charge, or electron number minus positron number in this theory, is conserved, imposing the most restrictive class of gauge symmetry, local gauge symmetry, as well as Poincare invariance and renormalizability, are the guiding principles for developing gauge theories like QED and QCD.